Hi, my name is Pedro and I'm here with Daniel, and we're going to do a screencast of our code for the second assignment of computer applications for unsupervised machine learning algorithms. So let's first start by analyzing our run file code, which is our main file. We'll start by analyzing our data. So let's first look at this data. This data variable represents the training set, and then we have the test set, which represents the testing set. So it's a list of points. Each point is comprised of a timestamp, which contains all the information of the grid. In our case, we have 9 bus bars, so it's a list with objects. Each object will correspond to a bus bar of a certain substation, which has the information of both voltage, angle, time, and the sub-RDF ID of the substation. This point will obviously contain 9 of these objects within the list. So in the first, in our training set, we have 200 timestamps. So we're going to have 200 points. Then we have our training set, which is exactly the same structure. We will also have some centroids and clusters. We're going to only assign 4 clusters, one for each state described in the project description. So let's start now with read SQL. Read SQL is simply gathering data from our SQL database. We simply connect to the main database, use the select all information from info, and info is going to be a string of measurements, and we're going to obtain all the information and build this our required database. And then we're going to initialize the data dimension of our clusters, which will be also the same as the dimension of our main data variable. So now we can start by going through our used k-means clustering algorithm and k-nearest neighbor as follows.
Okay, so to start the k-means algorithm, first of all we need to initialize some of our variables, initialize the algorithm itself. So to initialize the k-num, first of all we already initialize some values that we call centroids and some values that we call clusters. And then we already had our data set, our values already scattered in our space, which is a point, and a point is already discussed. It's an object of 9 bus bars, voltage magnitude, and voltage angle. Now we randomly or arbitrarily set our centroids, which is 4 centroids: high load, low load, line disconnected, and generator disconnected. We set this randomly to our space. Afterwards, we have to first start the first iteration, which is basically finding the distance between each point and the cluster. We do so by calculating the distance, the Euclidean distance, through this code here, and afterwards using that method that we created to get to know what is near, which point is near to which cluster. We use this algorithm to define the nearest point, the nearest point to the nearest cluster, and then we increase the index of that cluster. So we basically end up having a cluster of specific number of points. That's how we basically start the k-mean algorithm. But then that's not the whole algorithm. To continue this algorithm, we have to make a loop of different iterations. It starts with calculating new centroids by basically having the average of the old one, which is the points divided by its index number, and then basically going through a while loop that does nearly the same. The distance here calculated in the same way we did Euclidean distance, having the nearest algorithm part saying which point is close to which cluster, increase the index of that cluster, and basically storing the new centroids, the centroids here to an old centroid, and then calculating a new centroid. But this code will be forever, so we need to stop at a specific time. So basically, we will put a specific tolerance or threshold that if the distance between the old centroid and the new centroid is equal to that tolerance, or maybe less than the tolerance, the loop is done, and we basically get the clusters and indexes which we print. So yeah, that's basically how we initialize and finalize the k-means, and then we print our stuff. But now to start with the KNN, we have to actually label our clusters so we can assign names to our new data set that we're going to test. So now, yeah, labeling clusters.
Yeah, so let's start by looking a little bit at the code. Well, first, what we're going to do is we're going to look at shutdown of generator, then at line disconnection, which are the two cases or situations that it stands out the most. And then we're going to also label high and low load situations or clusters. So starting by generator disconnection, well, first of all, the condition for our generator disconnection is we're going to look at the generator bus bar and the bus bar connected to this one, which we just mentioned, and we're going to calculate the difference between these voltage angles, because the difference between voltage angles is quantitative representation of active power flow. So if there's no active power flow flowing out of a generator bus, it means that this bus will be disconnected. And this is exactly what this code does. So it loops through every cluster, looking for if there is any of these lines connected to generators which do not provide any or almost a negligible active power flow, which means that the difference between the angles of these bus bars has to be lower than this condition set here, so 0.5 milli. And this is the condition we set for generator disconnection. So after having classified this situation, we're now going to look at line disconnection. Well, line disconnection, the condition is we have to find the biggest difference of two connected bus bar voltage phasors. So we're going to have to look once again for each cluster, then we're going to have to look at the connection, all the lines, so the difference between these things. So it runs through this algorithm. We'll build complex numbers from their exponential form, and then we're going to do the calculations, and these must be higher than 0.2, this phasor voltage difference, which is the condition we set. Lastly, having labeled these two methods, the last one which we will do is simply look at high and low load. What we'll look at will be once again angles. So what we have to look at is we're going to look at the average angle of the whole system. So when it's low loads, the grid is usually capacitive, and when it's high load, it has a lagging factor, which means it's inductive. This has to do with active power flows. So we're going to do once again this classification, and we're going to calculate the difference, this average angles, and then the one which is the highest will be the load situation, and the lowest will be the high load situation during peak hours. Having labeled them all, the remaining step that we have is simply we're going to have to get once again the testing set using the same function, read SQL, and now Daniel is going to explain once again the k-nearest neighbor algorithm.
So labeling all the clusters now, we can basically go through the test dataset and say which cluster each new point that from the test dataset is actually connected to. So KNN. KNN is basically an algorithm. to classify things. So to start it, it's again a point of Euclidean distance. So first you set the new point in space, calculate all the distance to all the points that are around it, and then afterwards you arrange that calculated distance. So using this distance comparator from the library, or it's a method that we developed from the library, we basically in the descending order we put all these distances. So now we have the distances, but compared to what? Compared to the closest k number of points that we have, and we will define k as 20% of our data size. So basically, we will say that we will use the majority of the label. So let's say the majority label is low load, and for the k number of points that surrounds our new testing point, so basically this means our new testing point will be low load, and it goes on using this code to cluster them, which is basically what to assign for the new point. And that's basically how we go through our KNN, and finally we print every output, which I'll describe very quickly here. So basically we have quite some outputs here. To start with, we here have the centroids for each cluster, with each voltage and each angle for each point, for each centroids we have for each cluster. And then we have the number of index for each cluster, or the indexes basically for each cluster. And then the cluster points, or let's use the time instant that happened for that point. That's basically how we cluster them, and then how we label them. It's already described before, and these are the label for each cluster. And then KNN, you basically can see that the cluster number or index is increased from the k nearest to the KNN, and basically, and then we will print the new cluster with the new points. And that's it. Thank you.
Thank you very much.